This standard is about exponential growth and decay. We'll break this video up into 4 parts. First, we'll talk about exponential growth. We'll do some applications of growth. And then we'll talk about exponential decay and have some more applications. A very common equation regarding exponential growth is this one here, y equals 2 to the x. This is the equation you get when something's doubling. For instance, the penny we discussed in class. You start off with 1 penny, and then you double your money, and then that turns into 2 pennies. You double it again, it turns into 4 pennies. You double it again, it turns into 8. So let's make a table of what that would look like. I'm going to make an x and a y. So you start off with 1 penny. The way to talk about starting off is to say you're starting at x equals 0. So if x equals 0, you have 2 to the 0, and anything raised to the 0 power is 1. So on the first day, you have 1 penny. Well, first day, even though I have a 0, at the start, you have 1 penny. So after 1 day goes by, you double it. So that's x equals 1. So 2 to the 1 is 2. So after 1 day of doubling, you have 2 pennies. The second day of doubling, 2 to the 2 equals 4. So let's start to graph this. If x equals 0, y equals 1. If x equals 1, y equals 2. If x equals 2, y equals 4. So if you're thinking about pennies, it doesn't make much sense to think of negative numbers, but if you want to draw a complete graph, you do need to include the negatives. So let's also think about what happens if x equals negative 1. So then I have 2 raised to the negative 1 power. You may remember from our previous unit that anything raised to a negative power is the same as putting that thing in the denominator with a positive power. So this is the same as 1/2. If x equals negative 2, I'm looking at 2 to the negative 2, which is 1 over 2 to the positive 2, or 1/4. So if x equals negative 1, I'm down here in the middle. Negative 2, getting even smaller. You can imagine those fractions get smaller and smaller and smaller, but they're never really going to go to 0. You're going to end up with 1 over 10 million or something, which is a very, very small number, but still not quite completely 0. So when I draw the graph, I'm going to try and show that it's never quite touching 0. And then it's going to grow very large very quickly. Now let's look at an application of exponential growth. A baseball card bought for $50 increases 3% in value each year. What's its value after 15 years? So the general form for these kind of problems is the value is the initial amount times a base b, which is how much the power is changing, raised to the x. So in the last one, it was doubling, so b was 2. In this one, it's increasing by 3%. The percents are a little tricky. 3% written as a decimal is the same as 0.03. So how much is it increasing by each year? First, let's find 3% of $50. To do that, I would have 50. Of means multiply, so 50 times 0.03, which is $1.50. So after one increase, you would have 50 plus $1.50, or 51.50. A way to make that happen all in one step is if you just took 50 and multiplied that by 1.03. That would be 51.50. So the amount you're increasing by each year is 1.03 if it's a 3% increase. So the equation I'm going to write is the value is how much I started with, 50, and that's going to be multiplied by 1.03 raised to x, and x is going to be how many years. So after 1 year, you would multiply by 1.03. 2 years, it would be 1.03 squared, 3 years cubed, etc. So to find after 15 years, it's 50 times 1.03 raised to the 15th. 1.03 raised to the 15th is 1.56. And then 50 times 1.56 is $78. Exponential decay is like exponential growth, except things are decreasing instead of increasing. For instance, with this example, y equals 1/2 raised to the x power. You start out with something, and you take away half, and then you take away half again, and you take away half again. So it's going down rapidly instead of going up rapidly. So let's make a graph of this. We'll start by making a table. So we'll start by thinking about x equals 0. 1/2 to the 0 is 1. If x is 1, 1/2 to the 1 is just 1/2. If x is 2, you have 1/2 squared, which is 1/2 times 1/2, or 1/4. And let's think about negative numbers again, same as we did in the other one. So if I have -1, I have 1/2 raised to the -1. Maybe you remember from the exponent section that that means you can take what's inside the parentheses and take its reciprocal, and then raise it to the +1. So 2/1 is just 2, so 2 to the 1st is 2. If you have -2 for x, you have 1/2 to the -2, which is the same as 2/1 to the +2, or 2 squared, which is 4. So let's graph that. 0 is at 1. Kind of have to go back and forth a little here. 1 is at 1/2. 2 is at 1/4. 1 is at 1/2. 2 goes down to 1/4. And then what happens for the negative numbers? -1 goes up to 2. -2 goes up to 4. So these graphs start really big, and as time goes on, they get smaller and smaller. So this graph is getting smaller and smaller over time. Is it ever going to get to 0? It's not going to, same as the exponential growth one never got to 0. It's going to go 1/4, and then 1/8, and then 1/16, and then 1/32. The numbers are going to become smaller and smaller, but it'll always be 1 over something. So it'll never be 0, but it can become a very, very, very small number. Now let's try graphing a different one and see what we get. That's weird. So y equals 2 to the -x. So I'm going to make a table again. X, y. And you'll see why I picked this function in just a second. Let's start with 0. 2 to the -0 is just 2 to the 0, which is 1. If x is 1, I have 2 to the -1, which is the same as 1/2, or 1/2. 2, it turns into 2 to the -2, which is the same as 1/2 squared, or 1/4. And then negative numbers. If x is -1, I have 2 to the negative of -1, which is 2 to the +1, or 2. And -2, I have 2 to the negative of -2, which is 2 squared, or 4. So let's look at these two tables, the one with 1/2 to the x and 2 to the -x. You'll see that the y values are exactly the same thing, 1, 1/2, 1/4, 2, and 4. So both of these equations represent exponential decay, and if you'd like to think about it algebraically, 1/2 is actually the same thing as 2 to the -1. Raise that to the x power, and a power raised to a power you multiply. So 1/2 to the x is actually the exact same thing as 2 to the -x. So if you see a fraction raised to a power, or if you see a whole number raised to a negative power, either one of those represents exponential decay. Here's an example of an exponential decay application problem. Sarah has a collection of buttons to put on her backpack. She started with 250 buttons, and each day she gave 1/4 of them to her friends. How many did she have after 5 days? So she starts with 250. When she gives away 1/4, that means she's going to be left with 3/4. So each day she'll have 3/4 as many as she had the day before. So the equation for that, I'm going to say B for buttons, is she starts off with 250, and then she's going to have 3/4 raised to the power, I'm going to say D for days. So after 5 days, she'll have left 250 times 3/4 raised to the 5th, and that's 250 times 0.24, and that equals 60. So after 5 days, she would have 60 buttons left.